Welcome everyone to week 20 of Qubit by Qubit's Intro to Quantum Computing. Today we're going to be talking about both linear search and the Deutsch-Jozza, or I might sometimes say DJ algorithm. So these two concepts might seem a little bit disconnected at first, but I think the way to sort of think about this going into today's lab is that linear search is going to give us a chance to review algorithms, classical algorithms. I should mention, I guess, linear search is classical, Deutsch-Jozza is quantum. So the linear search will give us a chance to review classical algorithms, what they do, how they work at a very high level, as well as time complexity. So that's the big O notation that I guess we introduced very briefly earlier in the course, but we will go over again today. And then we'll talk about the Deutsch-Jozsa algorithm, which was introduced in this week's lecture. And we'll sort of compare and contrast the time complexities of classical and quantum algorithms to start giving you an idea of where quantum advantage comes from. That's really the point that we're trying to get at with this lab. And of course, in the process, the Deutsch-Jozsa algorithm is now our fourth official algorithm, or quantum algorithm that we've talked about. We've had superdense coding, we talked about quantum teleportation, although those two are pretty similar as we learned. Talked about QKD last week, and now we have a fourth algorithm joining us, which will be the Deutsch-Jozsa algorithm. Quick program for today, pretty standard. We'll have our usual Canvas attendance quiz and pre-lab Zoom feedback. There were no questions from last week that we came up with, although as always, if you do have questions that you want to ask, I am more than happy to try and cover them. Instead, we will just get right into the lab content after the pre-lab Zoom feedback, and then post-lab Zoom feedback as always. I should also mention, there is actually no optional content today. So, usually I would stay behind and sort of cover the optional content afterward. There's no formal optional content, but we're kind of anticipating that there will be a lot of questions because we're going to cover things at sort of a higher level in the required part. So if you want me to go into more detail, I am happy to do that in the optional section toward the end. Okay, Canvas attendance quiz. As always, lab number is 1. Quiz password this week is 6606. The question is, please rate your level of comfort with the 3 quantum protocols we've learned, I guess, so far. So as I mentioned, we have so far covered these 3 algorithms: superdense coding, quantum teleportation, and quantum key distribution. Each of those should ask you for a number between 1 and 5, where 1 is that you are not at all comfortable with the algorithm, 5 is that you feel like an absolute pro, and 3 is somewhere in between. So please give us your honest answer to these questions. This is just for our information. Of course, there is no correct answer, but please do the quiz because it counts for lab attendance. All right, let me pop up the pre-lab Zoom feedback. So I guess you just gave 1 to 5 responses for all of the 3 algorithms we've learned so far. Now I'm looking for your what did I say? You gave 1 to 5 responses for the 3 algorithms we've learned so far. Now I'm looking for your 1 to 5 response on the Deutsch-Jozsa algorithm in particular. And I guess anything else that Fran covered in this week's lecture. I will also open up the chat. So if you do have any, I guess, particulars you want me to go over, feel free to throw those in the chat. Although I think I will largely be deferring things to optional content if they're not already in my required content. Okay, so how about I leave that poll up for a little bit, and then I'll just quickly go over a more detailed agenda of what the lab will look like today. We're going to start off, as I said, with an overview of linear search algorithms. So the first couple here are going to be a review, right? So what is an algorithm? And we'll give an example of how linear search works if you as a human were to execute it. Those are things we have seen before, I think in optional content from a lab in the previous semester. So no worries if you don't remember this. That's why we're reviewing it and going over it again. And then we'll talk about the complexity of linear search, which is that big O notation, as well as hopping over to the IBM quantum experience. Although this doesn't actually require any quantum, we're still going to use that same environment to code linear search. Then in the second half, and actually this will probably take more than half, so hopefully I can do kind of 20 minutes on the first part, 40 minutes on the last, that kind of thing. we'll be talking about the Deutsch-Jozsa algorithm. So what problem it aims to solve, how it solves it. We're not going to be going through the math of it per se in the required content, but I am going to give you sort of a high-level overview of the various steps in the algorithm and how you can think about it working at a higher level. So hopefully that'll just provide a little bit more detail than what was given in the lecture on Sunday. Okay, so before we move on, let me end the concept poll and I will share the results. So I think generally this reflects a slightly lower level of confidence, which is okay. Hopefully the other thing is once you see me go through everything in the lab, you have some sense of what level of understanding is actually required, right? Like if you follow everything in the lab, then you're doing fine. Of course, we can go into more detail in the optional content, but it is optional. Okay. Let's first do our couple of review slides on algorithms. Like I said, these were slides that we have seen before, so this might look familiar to some of you, but no worries if it doesn't. We talked a lot about quantum algorithms so far. Of course, algorithms in general are a thing that exists for both quantum and classical computers. And the definition of an algorithm at the highest level is just that it's a set of steps to solve a problem. So you can think of it with starting off with some kind of problem. In this first example, when we do linear search, the problem is going to be, hey, find a particular element in a list, right? So if I gave you a phone book, for example, and I wanted to know if my phone number ever appears inside that phone book, that is, an example of a problem. It's a question that I ask that does not have a super obvious answer. We feed that into an algorithm, which, like I said, the definition is just a set of steps. So it's going to give us, step 1, step 2, step 3. Maybe there's going to be some conditionals like, if this thing is true, then skip to step 7. Or maybe there's going to be some loops like repeat steps 4 through 6 10 times, stuff like that, that we can go through. And at the end of all these steps, we should somehow be able to produce a solution to our problem. Let's look at this concrete example of linear search. So whenever you talk about algorithms, you should usually start off with a problem statement, just to sort of set up what problem you're trying to solve. And I guess it is sort of like this diagram showed on the previous slide. You start with your problem, you talk about the steps that you're going to use to solve it, and then usually you'll want to walk through a full example to see how you get a solution. So we're going to start off with a problem. And the problem is to find the student whose age is 19 years old from the following list. And then suppose you're provided with this big long list of student names and ages. And these aren't sorted in any particular order, as you can tell. We've got 17 at the top, 15 at the bottom, and a bunch of ages in between. So I guess the question that you can think to yourself is, how would you find the student whose age is 19 years old from this list? Hopefully, it's sort of a fairly straightforward question. I don't mean to be tricking you here. Probably what you would do is just start checking, right? This is a small enough list that you probably just did this on your own without thinking about it. But essentially what you're doing in your head is you're looking at the first element and you say, okay, is this person 19 years old? No. All right, let's move on to the next one. Is this person 19 years old? No. Okay, move on to the next one. And then you would keep checking these in sequence, right? So going in order. I mean, you don't have to go from top to bottom. You could go bottom to top or whatever order you want, as long as you end up checking every single element until eventually way down here, we get to Brian and we see that, yes, Brian is 19 years old. And so we can say, yes, Brian is the one whose age is 19, and that's our solution. So a couple of things to note here. First of all, we are, as I sort of mentioned, we're going through and checking each element in the list one by one, right? So in order to cover off these first 7 elements in the list, I needed to do 7 checks, right? Because I need to check every single one. But when I get to the actual solution, down here it was Brian, I don't have to go keep checking the rest of the list, right? I just say, oh yes, there is one student whose age is 19, it's Brian, here we go. And I end the algorithm there. And so we know we don't have to go on and check the rest of the list. As I mentioned in the algorithm slide, we start with a problem, then we typically give a list of steps. And so that's how we're going to define our linear search algorithm. So linear search is sort of the most basic way you can search a list, and it goes exactly as I just described. You start off with the first element of the list and sort of one by one compare X, or I guess this is the target, so whatever target age you're going for, compare the target age with each element of the data set, right? So that's what we're doing. We're comparing 19 to each of the ages in the data set to see if they're equal. Okay, step 2, if X, the target, matches with the current index, then we return it, right? And return here is just in the sense of a function, like a Python function, returning a value. If X does not match the current element, so that's what happened for the first 7 elements that I went over, then you just move on to the next one, as I did. So I checked the first one, doesn't match, move on to the second one, and so on and so on. Now, one case that we did not see with my previous example is if X doesn't match with any of the elements in the array, right? Maybe we only had those first 7 students in our list, and we got all the way to the end and realized that none of them have age 19. Then what we're going to do is we're going to return -1. And that's just going to, it's kind of like a flag or a signal. It doesn't literally mean that, oh, we found someone whose age is -1, right? Clearly that can't happen. But this is just a signal to us that says, the element wasn't found or the search failed for some reason. Let me just check the chat. So somebody asks, yeah, what if there are 2 or more people aged 19? I guess it depends on what exactly your problem is. Perhaps we should have been more specific here and say, find a student whose age is 19 years old from the given list, right? And so that would imply that returning any student who's 19 years old would be a valid solution to the problem. And so then you can just stop when you find the first one. You don't have to keep looking for if there's more. Yeah, and that is what people said in the chat. Of course, you could imagine modifying this algorithm if you wanted to find every student whose age is 19 years. Then, as was alluded to, you can't stop when you find the first one, right? You would have to keep checking the rest of the list to make sure that there aren't more students whose age is 19 years old. Okay, so the point of going over this example, linear search, it's not supposed to be super complicated. It's supposed to be a fairly straightforward way to search a list and sort of give us a template for how we talk about algorithms, right? Again, we started with our problem, and then we gave this nice list of steps that you can follow to answer any version of that problem. The other reason we wanted to talk about algorithms, though, is to go back to big O notation. So big O notation, before I get into the details of this, at a high level is trying to tell us how performant an algorithm is. So if I asked you about the performance of linear search, possibly the first thing that would come to your mind is how long does it take, right? How long does it take for a Python program that executes this linear search algorithm to find an answer in a list of, say, 1 million students, right? If we have this really big list, maybe it's going to take a Python program 4 seconds to go through a list of 1 million students and find an answer. That's not usually the way that computer scientists talk about performance, though. Usually when we talk about performance, we are not so interested in what happens when you try to solve one particular problem on one particular computer, right? Because obviously it would take a different amount of time, or it could take a different amount of time to solve a problem with 1 million elements, or to solve a problem where the element you're looking for is the very first one. And it doesn't matter how large your list is. Or maybe I have access to a supercomputer and it can scan through 100 million elements in half a second, right? So there's all these other variables that affect how long in seconds an algorithm takes. So computer scientists come up with another way of talking about the performance of algorithms, and it's called big O notation. And it effectively tries to account for these other variables to come up with a more consistent descriptor for how performant an algorithm is. The way it does this is by looking at how the time required to do an algorithm scales with the size of the problem. So in this case, we're going to look at the most general case. If the list has n students, right? And then we'll ask ourselves, how many comparisons, how many checks with the target do we have to do in the worst case? So this worst case piece is just part of the definition of big O notation. So as I mentioned before, if the student you're looking for, the age 19 student, happens to be the first one in the list, then of course you do one comparison, you return that, and you're done. Easy, right? But we're asking what happens in the worst case with a list of n students. And what happens in the worst case is you don't find the student you're looking for, right? You go through, you check every single element, and you have to check every single element by the way our algorithm works, only to find out that there is no student with age 19, right? And in that case, you have to perform n comparisons, where n is the number of students in the list. So this number that we come up with, the number of comparisons that you do in the worst case, is called the big O complexity of the algorithm. It's a little bit more complicated than this if you want to do the sort of full mathematical definition, but this is a perfectly valid and reasonable way to think about it. You think about a general problem, right? So in this case, a list with n students. We don't know if the target is in that list or not, or if it's at the top or the bottom of the list. We're trying to keep things general. It has n students. And then we ask ourselves, how many steps are there going to be in the worst case? And here, there would be n such comparisons. When you see this written, you'll often see it written as, this is why it's called big O, capital O of n. So we pronounce this, big O of n time complexity. Sometimes you'll also hear it just called linear because this value in here is linear versus something like big O of n squared, which would be quadratic in complexity, and so on and so on. Okay, that brings me to the end of, I guess, the theoretical discussion of linear search. Next, I'm going to hop over to a Jupyter notebook, and we'll actually code this and see how it works. We have one question in the chat before I move on. Is the worst case a 19-year-old student being on the last row, or are they equivalent? Yeah, so the two worst cases, I guess, are either the student you're looking for is the very last one in the list, so you have to check everyone before them, and you have to check that student before you finally know that that student has age 19. Or they don't exist in the list, right? And you still have to check every single element before you find out that nobody has that age. Some people are also asking me to explain what oracles are. I will get to that when we talk about Deutsch-Josza. Okay, so I'm gonna hop over to the IBM Quantum experience. Coding this linear search algorithm is not going to take us very long. It's, as I said, fairly straightforward. Okay, oops, I'll scroll up to the top. So the only thing we have in our IBM Quantum experience notebook this week is going to be the Deutsch-Josza, is going to be linear search. We're not going to look at Deutsch-Josza in the IBM Quantum experience unless you want me to look at that. Okay, so quick introduction. We talk about a search algorithm. We talk about these two things called sequential and interval search. I didn't cover that, but you can read about this if you are curious. We still have enough information to go ahead. This section on linear search basically describes in words what we just went through, where you're checking each element of a list. And so the first thing we need to set up, much like in the slides, is our problem, right? So in this case, I'm going to go ahead and grab a sample data set. So this is not the same one that we saw in the slides, but we will use it as an example. So here we go. I have just put in a list, so you can pretend this is a list of ages, right? I guess 109 is a bit old, but pretend this is a list of ages. And suppose our target, so we're looking for someone whose age is 14, just as an example. Just for our information, when we were talking about big O notation, we talked about n, right? So I'm just going to write that down for ourselves here. N is just the number of elements that we're trying to search through, right? And so in Python, we can do len, which is short for length of data, and that will give us the data set size. Okay, so just for fun, we can print out whatever n is. And so when I run this cell, we should see, okay, we have 15 ages to search through. So far, so good. Okay, here is the same sort of 4 steps that I talked about on the slides. So again, I won't go over this again. But we now want to write this as a Python program, right? We know how it should work in theory. Now we want to write it down with code. Okay, let's go into our function here. We're going to define a function called linear search. It's going to take 2 arguments. The first is going to be the list of data that we want to search through. And then the second is going to be x, or our target. First thing we're going to do is to find the length. Oh, whoops. Indentation is weird here. The first thing we'll do is to find the length of the data set. So again, I'm just going to call that n. And as we saw above, that can be computed as length of data. Okay, so the next thing we have to do is scan through every single element of the list, right? So I'm going to do that with a for loop. So we'll say for I in range n. And what this is going to do is it's going to loop us through every value of I. So in the first iteration, I will equal 0, then I will equal 1, then I will equal 2, and so on and so on. And then the final one will end with I equals n minus 1. Now, the reason we have n minus 1 here is just because we started at 0, right? And so if there's n things in the array, we start at 0, the last index is going to be n minus 1. So once we're inside this loop, we're going through each element in our list. What do we want to do? Well, you can see I'm kind of following the guidance of these comments. We now want a conditional to check or to compare our target with the current element in the array. So a conditional in Python is just going to be an if statement. And I'll just say if the target, x, and remember that's an argument that we're given up here, if x is equal to, and we use double equals for this in Python, data at I, right? And so this is just going to look at the ith element in our data. So again, that'll start with the 0th element or the first, then it'll check the second element and the third element, and so on and so on. Okay, and as is alluded to here, if we do find our value, we will return 2 things actually from this algorithm. We will both return the array element itself, or sorry, not the array element itself, the index where we found the array element. So for example, if we found it as the first element in our data set, we would find an index of 0. If we found it as the 5th element, we would find an index of 4, etc. And then we're going to return a second thing from this as well, which is the number of steps that we've done. So the number of comparisons. The index we found is pretty straightforward. That's just going to be I. The number of comparisons we've done in this case is actually going to be I plus 1, just because, again, I starts at 0, right? So when I is 0, we have performed 1 comparison. When I is 1, we will have performed 2 comparisons, and so on and so on. Okay, so this loop is then going to repeat n times. It's going to check every single element in our array. And if we ever find the target, we're going to return it. Otherwise, if we never find the target, well, we need something to do here. As I mentioned in the slides, our convention is going to be to return -1. And then, just to remain consistent, we are also going to return the number of steps, which again, in this case, is just going to be I plus 1. Okay, so let me just pause and check the questions if there's anything I need to address. Yes, we will look at Deutsch-Jozza in just a minute. I'm almost done with the linear search stuff. Somebody asks why we only consider the worst case for big O notation, and what about the remaining cases? We actually have a Zoom poll question coming up about that exact topic, so sit tight. Yes, so target is the age we're trying to find. Code, please, is 6606. Yes, I'm sorry. I will put that up here. And cool. Okay, so, and yes, returning -1 is just a convention. You could set up some other system, but this is going to signal to our, whoever's calling this function that we failed to find the element. All right, let's move on. Oh, actually, I need to run this code block, I guess, make sure we have our function. Okay, and now we are going to go ahead and try running this function. So actually up above, I think I said the target was 14. I guess we'll look for 19 instead. And then we're going to go ahead and call our function. So we want to get the result and the steps. Our function is called linear search. And then to pass in here, we're going to pass in our data, which we defined in one of the previous cells, as well as x, our target. And then it's going to print out if the element is present at index blah, and the result was found in blah steps. Let me go ahead and give this a run. Okay, so we have that the element is present at index 11. Let's go back up and just double check that that is true. So looking at our original data, we can see that, yes, 19 is here. And I'm just going to assume that if you counted up what index this is, it would be index number 11. And it also tells us that there are 12 steps. It's always good to test things, so we can try this out with different values of x. If I did go to my original value of 14, for example, and I run this, now we see that there was a different index found, and it took slightly fewer steps. Versus if I try and look for something that is way too large, we don't have one of those, we should see, there we go, that we get -1, and it took 15 steps. So again, the full length of our list was 15. It took 15 comparisons to figure out our answer in this case. All right, so let me throw up a Zoom poll for these questions down here. There's 3 of them, and it kind of relates to the question that I mentioned earlier, where a student asked about, why do we consider the worst case? It's kind of just a convention. It turns out to be most useful in a lot of cases to consider the worst case, but it's perfectly reasonable to consider the average case, for example, as we do in question 3 here, or even the best case, as we do in question 1. So I'm going to throw up a Zoom poll, and I will give you all some time to think about the best, worst, and average case complexity of linear search. And I guess just to give one piece of clarification here, the number of steps that we're looking at is the number of comparisons, right? So how many comparisons you would have to do. Interesting. Some people are saying that they can't submit the poll. Yeah, so this is a multi-question poll. Maybe that changes the way that it shows up on your screen. I'm not 100% sure though. Yeah, okay. Thank you to those of you providing some live tech assistance. Okay, so about 50% of you have submitted your answers. If you haven't yet, no worries. I'm just going to start talking about some of these answers. Let's begin with question number 1. What is the minimum number of steps that would be required in linear search? So this is something that I sort of alluded to earlier. Think about so again, the way to set up this problem in your head is to think about a general list of length n. It's general though, because you don't know where the target is. You don't even know if the list has your target, right? And so all of these are cases that you want to consider. So in this first question, what's the minimum number of steps that would be required? Well, we're going to scan through the list starting with the first element, and we're going to make a comparison. So we always have to do at least one step, right? Unless the list is empty, I guess. That's an edge case that I just didn't think about. But yeah, you always have to check the first element. In the best case, you check the first element, and that's the element you were looking for, and now you're done, right? You can immediately return and say, that's the element I was searching for. And so indeed, this algorithm can finish in only one step, and that occurs when the target is at index 0. So that's the answer to the first question. The second question is what we went over in the slides, right? The worst case or maximum number of steps. Now, for this one, you could, in theory, check every single element in the list once, right? And that would be to make n comparisons. So we would have to do n steps. And I said in the slides that that occurs when your element does not appear in the list. That is a valid answer. The answer that we were looking for in the poll here was that the target is just the last thing in your list. So again, you would have to scroll through and check every single element in the list before finally coming up with your answer. Okay, let's look at question 3 then. So somebody asked me to specifically talk about this one. What is the average number of steps that would be required for linear search? So this is not a straightforward question to answer, right? Because when we're talking about the average number of steps, we're kind of saying like, oh, consider any possible list of length n and a whole number of different targets that you could search for in that list. And now take an average over how long all of those would take. I'm not going to give a formal way to prove this or to think about this, but generally speaking, you can think about it as, okay, if I was looking for a random element in my list of n ages, what is the average position of that element, right? If I picked a random one, sometimes it might be really early in the list. It might be the first or second element. Sometimes it might be really late in the list, one of the later ones. Sometimes it's going to be in the middle. Sometimes it's going to be elsewhere. But on average, where is the average position of my target? In the middle of the array, right? Just because that's the average position of all elements in the array. So this one's a little bit tricky to think about. But for this, the average case is when your element is right in the middle. And in that case, it's going to take you searching through half of the list, or n over 2 steps, before you hit that target. Yeah, so somebody's asking in the chat, doesn't this basically boil down to the expectation of the number of steps if you treat the number of random steps as a variable? Yes, that is perfectly valid and a great way to think about it. In fact, that is the sort of more mathematical and proper way to think about these things. Somebody asks, why isn't the number of steps n over 2 plus 1? I guess it could be. It depends on exactly what case you're looking at. I think for this particular question, I wasn't trying to be too specific, but it could be n over 2 plus 1 for, I guess, odd. Well, yeah, it depends on the size of the list, I think. Okay, so yeah, let me go ahead and show the answers to the poll here. That does mean I have to end it, but I have gone over all the answers at this point. And share. There we go. So people seem to be fairly confident on the first two, maybe a little bit less confident on the last question, but still pretty good. So good job on that. Final little piece I wanted to mention here in the notebook is just on big O notation. So even though we just did this question with best, worst, and average case, whenever we talk about big O, we're talking about the worst case. right? And so the worst case was n steps when you find the element at index n minus 1, or when the element is just not in your list. Okay, so the only other stuff in this notebook is the extra content, which is not even part of the optional content unless you want it to be. So for the time being, I'm going to go ahead and hop back to the slides, and we'll talk about Deutsch-Jozsa. Okay. Cool. So like I said, that's the end of everything on linear search. We have talked about its complexity. We have coded it, all that stuff. So let's move on then to the Deutsch-Jozsa algorithm. Now, this is separate from linear search. It doesn't really look like linear search at all. Again, the point of talking about linear search was to review algorithms and big O notation. Just like we did with linear search, the way we're going to introduce the Deutsch-Jozsa algorithm is to begin with a problem statement. And in order to understand this problem, I'm going to use an analogy, as usual. So some of you might be familiar with the story of Goldilocks and the Three Bears. If you're not, that's okay. I'll explain as much as you need to know for this. There's some random cover art for it. Anyway, in one part of the story, Goldilocks, who's kind of like the main character, wants to figure out if a soup is too hot, too cold, or just right. So there's kind of these, it's an extreme temperature or it's balanced, right? The Deutsch-Jozsa algorithm solves a very similar problem, but it's going to sound a little bit more mathematical. The Deutsch-Jozsa algorithm asks whether a function is too hot, it's a typo, too hot or too cold, so some extreme constant, or if it's just right, which would be balanced. I'll give an example of this in just a moment. But before we get into it, I do want to note that this is what we call a toy problem. In other words, it doesn't, as far as we know, it doesn't have any practical uses in the real world. Unlike, for example, superdense coding, quantum teleportation, or QKD, all of those things could potentially have real world implications. The Deutsch-Jozsa algorithm probably doesn't, right? But it was designed, and the way that the reason, that we still learn it is because it's specifically designed to demonstrate by proof of existence that some algorithms run faster on quantum computers, right? So this is going to be an example of a problem, this Goldilocks constant balance problem, that a classical computer is going to take way longer to solve than a quantum computer. And we're going to look at exactly why that is. Okay, so let's do the more mathematical version then. Suppose we have a function f of x, which takes as input a binary variable x. So we are going to only look at the case where where x is 1 bit. So x is going to be 0 or 1. But you can do this for any arbitrary binary inputs as well. So you could have it take a 8-bit input, for example, totally valid. Okay, the function is also going to return a binary number for each input value of x. And it's only going to be returning, again, 1 bit. So it's going to return 0, or it's going to return 1. So pretty simple function, takes in a single bit, spits out a single bit. Now, if you think about all the possible functions f that do this, there's actually only 4 of them. It's quite limited. And those 4 possibilities are these ones. First of all, we could have that f of x always spits out 0, no matter what you put in. On the other hand, we could have it always spit out 1, no matter what you put in, right? So again, these tables fully define the function f because we're only taking a single bit as input. So we're either going to get 0 or 1, and so we're only going to have 2 possible outputs of the function f. There are 2 other possibilities. We could simply spit out x itself, right? So we could always return precisely x, or we could always flip x, right? So here x would be flipped to 0, and x equals 0 is flipped to 1. I introduced these terms in the previous slide, constant and balanced. we can label our four possibilities here as either constant, in other words, the value of f never changes, right? So it's either always 0 or always 1, or balanced. It gives 1 half of the time and it gives 0 half of the time, right? So again, here we're looking at the output columns to see whether our function is constant or balanced. Okay, with all of that setup done, time for the actual problem statement. This is the problem that the Deutsch-Jozsa algorithm is going to solve. Can you figure out if a given function f is constant or balanced? Right, so I'm going to give you essentially one of these four possibilities. You're not going to know which one it is. I'm just going to give you, some box that implements f. So you can drop in a 0 and you'll get an answer, or you can drop in a 1 and you'll get an answer. But you don't know which of these four it is. And the only question I'm asking you is it constant or balanced? I don't need to know exactly if it's 1, 2, 3, or 4. I just need to know if it's constant or balanced. So the whole point of this is to try and compare classical and quantum algorithms. We're going to start off then with the classical solution. So I'll pose this problem to you. How would you solve this problem classically, right? And this is sort of the way that you would solve it as a human as well. If I just gave you, some random box that implements this algorithm, how would you go about determining if it's constant or balanced, right? Well, you don't really have that much choice, right? Probably what you'll do is you'll try feeding in x equals 0 first, and you'll see what happens. And suppose that our function spits out a 1. Okay, so now by process of elimination, I know it can't be the first one, because then it would have spit out a 0 for x equals 0, right? I also know it can't be the third one, or I'm sorry, can't be the fourth one. Or no, third one, I was right. Because then it would have spit out a 0 when I put in x equals 0. But I still have two possibilities, right? It still could be the second f or the fourth f. And the question I'm trying to answer is whether this thing is constant or balanced. Well, we still have one possibility that's constant and one possibility that's balanced. So I still don't know the answer. I need to do a second trial. And so I would have to feed in x equals 1 and see what the answer is. And suppose here I get 0. Now I can eliminate choice 2, and I know for sure that my function is balanced. Now you can work this through with different examples, and you should be able to convince yourself that no matter what this function f is, whether I give you 1, 2, 3, or 4, you're always going to need to do 2 evaluations of f to figure out if it's constant or balanced, right? If you only did 1, like in this example, when I just plugged in x equals 0, you're always going to get something that does not give you quite enough information to determine if f is constant or balanced. So that's what the rest of this slide says. You have to test the output of the function, test out the function, with inputs 0 and 1. So you basically need 2 steps to do this. Now it's still pretty good, right? You can still solve this question with only 2 steps. As you might guess, the quantum solution is going to be better, which implies that the quantum solution is going to need probably just 1 step. And that turns out to be true. When we go to the quantum world, we can do this with just 1 evaluation of f. Sounds weird, but it is indeed possible. Okay, before we talk about the quantum solution to this problem, I guess at the end of the day, we want to create a quantum circuit to solve it, right? It's not entirely obvious how you implement f of x as a quantum circuit, though, right? How exactly are we going to do this whole f of x business with qubits and with h gates and c0 gates and all that kind of stuff? It's not entirely obvious. So we need some way, and this, by the way, is not just for Deutsch-Jozsa. This is something you have to think about no matter what your quantum algorithm is. We need some way to implement this f of x function in a quantum circuit. And this problem is a little bit difficult in the world of quantum computing because everything in quantum computing has to be reversible. So remember, we talked about reversibility, I guess, a couple of labs ago now. But it basically means that if you feed a whole bunch of inputs into a quantum circuit, and you see all of the outputs, you have to be able to reverse engineer what the inputs were with perfect certainty, right? So if I just give you the outputs from a circuit, there should be no ambiguity as to what the inputs to that circuit were. My question to you then is f of x reversible? In other words, if I give you the output from a circuit, do you always know what the input was? So think about that for a moment. I don't actually have a Zoom poll for this, but just think about that for yourself. People are saying, no, no, not always, okay? That's correct, right? And I guess I probably implied the correct answer as I was setting this up. But now I'll ask the question, why, right? Why is this not reversible? Let's look at, possibility 0, or I guess I'll call it 1, right? So for possibility 1, what does it mean to be reversible? Well, it means that I will give you the output. I'll tell you that, hey, f of x equals 0. What's x? Right? And in this case, you don't know, because x could have been 0 or 1 to produce that result. And so just by looking at this first case, we can immediately say f is not reversible, because I can't answer that question. If I tell you that f of x is 0, you cannot tell me what x is. As someone mentioned in the chat, there are some cases, notably 3 and 4, where you can reverse f. But because there is one example where you can't, we're going to say that this function is not, in general, reversible. So just to recap, in order to do the quantum version, we need a quantum implementation of f of x. But everything in quantum must be reversible. And f is, by default, not reversible. So in order to fix this, we're going to have to create some kind of quantum version of f that is reversible. And that is where the oracle comes in. Just to restate the problem, we have quantum gates, which always need to be reversible. F of x is not reversible. And this problem happens to come up quite a lot, not just in the Deutsch-Jozsa algorithm, but in all kinds of other quantum algorithms, where you have some kind of function or procedure that you want to use in a quantum algorithm, but that function or procedure is not reversible. And so you need to come up with something called an oracle, right? And this is where the concept of oracles comes in. It's basically how we solve this problem, how we take an irreversible function, turn it into something that is reversible so that we can then implement it on a quantum computer. So when we talk about oracles, we often sort of reframe the function as a genie that's going to give you answers to any question you give it, right? And this is really just a reframing of the exact same concept of a function, right? A function is kind of like a genie in that I will give it something like a 0, and it's going to spit out an answer, right? And I can give it something else, and it'll spit out maybe the same answer, maybe something different. Pretty straightforward idea, but just sometimes you will hear people talk about these things like they are, a genie giving out answers, but it's really just a reframing of the same idea. So oracles are kind of a famously hard thing to wrap your head around, even in classical computing. Oftentimes, algorithms that involve oracles are quite a bit more difficult to analyze. When you go to the quantum world, quantum oracles are even more difficult to wrap your head around. And so it's perfectly all right if this doesn't make sense on the first run through. I'm going to do my best to try and explain it, though. I do think that it's good to sort of think about oracles as this genie, right? So it's this all-knowing being that you can ask a question to and it'll give you an answer, right? We don't really care how it does that. We don't care how the genie is made. We just care that it does give us some answer for every question we ask it. Now, ultimately, and we can talk about this in optional content if you want, but ultimately, an oracle is just a fancy quantum circuit, right? You can write it as a single matrix and you can decompose it into gates, but we usually don't really think about that because that's just going to complicate our life. So we're just going to think of it as a thing where you feed in one input and it gives you one output. And I guess just a note, oracles are used all over the place in quantum algorithms, notably in Deutsch-Jozsa, as we're going to see in a moment, and in Grover's search, which we're going to see next week. Okay, so let's talk about the Deutsch-Jozsa oracle, as it's called. So again, this is just a recap. Since f of x is not reversible, this whole oracle business comes about because we want to do irreversible things on a quantum computer somehow. So since f of x is not reversible in general, we need to make a reversible version of it for our quantum algorithm. I'll note here that there are many different ways you can do this, right? So there's many different ways you might be able to think of that make f of x reversible. I'm going to present one here that happens to work well for the Deutsch-Jozsa algorithm. Not really going to go into how you might derive this, but this is one possible choice of oracle that happens to make our algorithm easier to think about. And it looks like this. So let's talk about how this thing works. The first sort of line here is the easiest, right? If you plug in an input ket0, it's going to spit out as an output ket0. Pretty straightforward, right? Whatever you pass in, it just spits out the exact same thing on the first output. The second lines are a little bit more interesting, though. We introduce this new variable y, and our output is going to be y XOR. So remember, this plus with the circle around it is XOR. Y XOR f of x, right? So again, there are other ways of doing this that might seem simpler. For example, maybe you just want to spit out f of x itself because that's what we care about. But no, here we're going to do an XOR with y. Let's just go through a couple of examples. Suppose that my function f of x is the constant version that always gives a 0 as the output. So no matter what my input is, my output is always going to be 0, right? Then what would happen? Let's walk through some examples here. I could start off with ket0 as my input. The first output, as I said, is easy to determine. It's always going to be just the first input. For the second one here, I have to do a little bit more work. So 0 XOR f of 0, right? Just plugging in my values for x and y. Then I will evaluate f. So f of 0 is going to be just 0. Then 0 XOR 0 is still just 0. So my output here is going to be ket0. Again, we're not worrying about how this would actually be done with gates. We're just pretending that this is a genie sitting inside this UF box, and it's going to automatically produce the correct outputs given whatever our input is. Okay, let's change this up. Maybe we'll do ket1 down here instead. So now my first input has stayed the same. Therefore, my first output is going to stay the same. To do the last output, I need to do a bit more math. So y is 1 XOR f of 0. Again, just plugging in the values for x and y. Just like before, f of 0 is 0. But now 1 XOR 0 is 1. And so the output in this case would be a ket1. So you can, of course, go ahead and do this for a bunch of different possible inputs, and you will always get some valid output out of this gate. Once again, just to sort of emphasize here, there are many possible ways you could construct a reversible version of f. This one is the one that we're going to use just because it makes the Deutsch-Jozsa algorithm a little bit easier to see. Okay, now I'm going to leave this check as sort of a problem that you can take home if you want to try it, but you can check that this oracle is reversible. The way that you would do that is if I give you outputs, right? So if I tell you that the output is ket0, ket1, you should be able to check that you can always get the exact inputs as well, no matter what version of f we're using, right? So whether we're constant or balanced, you can always reverse engineer this thing. It might take a little bit of time because you have to go through sort of 4 cases for all the different versions of f, but you would indeed find out that this thing is reversible. And just a little hint for you that might be a useful formula during that proof. this is always going to be true. If you have y XOR f of x, XOR f of x again, these two XORs at the end kind of cancel each other out, and you're always going to get y. So if you're interested, you can use that to prove that this is reversible. But I won't go over it here. Okay, the last thing that I will, again, sort of glance over, but not go into too much detail on, is to think a little bit about how you would actually implement this oracle, right? Again, it's totally valid to just think about it as a genie that magically produces the correct quantum states. But of course, if you were to run this in a real lab, you would need to implement this genie somehow. It turns out this oracle is actually pretty straightforward to implement, although it can be kind of tricky to think about exactly what it would look like because this last output is kind of confusing, right? Again, I'm not going to go through the exact solution right now, but just to give you a little bit of a hint, if you wanted to look at this yourself, the oracle uses an XOR, right? This last output here, the more complicated one, uses an XOR. Now, we don't have an exact XOR that we, in quantum computing, but we do have something that's very similar. So I'll give you a moment to think about it. Remember that the truth table for an XOR is the following. Right? So it's going to be 1 if the 2 bits are different and 0 if the 2 bits are the same. Is there a quantum gate that does something like this? Right? It's not exact, right? Because there's no quantum gate that we've learned that takes 2 inputs and gives only 1 output. But there is a gate, as some people are saying, that does this for one of the outputs, which is C naught. So if you actually write out what C naught does, it copies X to the first output, and then the second output is exactly Y XOR X. Now, the other ways that we've talked about C naught are totally valid. This is just another way that you can think about the C naught gate. It turns out to be useful if you're implementing this particular oracle. Okay, so let's look at the Deutsch-Josza algorithm then. As I alluded to before, this is going to let us solve this problem of balanced or constant function in only one step. The algorithm is going to use both superposition and interference. And I'm just going to walk through some of the steps here. Again, I'm not going to go into detail on the math in the required portion. We're going to start off with a quantum circuit of 2 qubits, X and Y. And actually, as we go through this, I'm going to just draw out a little circuit diagram here on the right. So we start off with 2 qubits, X and Y. Step 2, apply an X gate to the Y. Okay, that's just an algorithm, whatever. Step 3, now we apply H gates to both X and Y. Okay, so we have an H on the X, and we also have an H on the Y. Now, as you might remember, H gates create superposition. So it's in this step that we are sort of taking advantage of superposition as a property of quantum computers. Then we're going to apply the oracle to X and Y. So remember that oracle that we looked at takes 2 inputs. So I'll just have a big UF here. It's going to take both of these as inputs, and it's going to spit out 2 outputs. And remember, in this case, we don't know exactly which version of F we're using, right? Someone's given us this genie that's going to tell us answers, but we don't know if it's constant or balanced. Step 5, we're going to apply H gates to both X and Y again. So in my opinion, the best way to kind of think about this is it's sort of undoing the superposition from before, but not exactly, right? Because we had this UF in between. So the UF is going to modify our state slightly. But when we apply these H gates again, they are actually going to cause the superposition that we created in the beginning to interfere with itself, right? So it's kind of the idea like from the double slit experiment where you can have things interfering with themselves. Hard to think about, but that's sort of what's happening in this step. And then the final step is that we're going to measure X. So I'll do my best attempt at a measurement diagram here. And then if the result is 0, the oracle is constant. And if the result is 1, then the oracle is balanced. And we're done. That is the Deutsch-Jozsa algorithm. And if you go and look at the full details of this, you will find that you get this answer with 100% certainty. And note, we only had to apply the function f, which again in the quantum world is this oracle thing. We only had to do it once, right? Another way of looking at this is when you look at the circuit, there's only one UF block, right? We only have to evaluate f of x once. So that's where the Deutsch-Jozsa algorithm gets its advantage, right? It only has to do this one step, whereas usually you would have to do 2 steps in the classical world. Okay, this is the final slide I have before we wrap up. I know that we are just about at time, but this is just to really drive home that point about the quantum advantage. For this simple 1-bit input case, so remember here our f of x only takes 1 bit as an input, but I said you could take arbitrarily many bits as an input, and so this algorithm can get more complicated. In the 1-bit case, the classical algorithm takes 2 steps, and the Deutsch-Jozsa algorithm uses just 1 step, right? Now, it turns out that the best way to do this in the classical case is quite inefficient, because you have to end up evaluating a lot of the different inputs to f. So if we had, for example, an n-bit input, right? So we'll just say 10, for example, right? If you had a 10-bit input to your function f, there are 2 to the 10 different inputs you could try, right? In our 1-bit case, we could either feed f0 or 1. But if you go up to 10 bits, you could feed it all zeros. You could feed it 9 zeros and then a 1. You could feed it 8 zeros and then a 1 and a 0, and so on and so on. And there are actually over 1,000 different combinations of inputs you could feed into that function. And in the classical version, you have to just keep feeding in numbers until you can conclude with certainty that the function is constant or balanced. That takes big O 2 to the n steps, right? So again, here is the size of our input. It's n bits. It's going to take, in the worst case, 2 to the n steps. The Deutsch-Jozsa algorithm, we didn't talk about how it scales to more qubits, but no matter how many qubits you have, it always takes 1 step, which is like super surprising, right? You can have these huge functions that take thousands of bits as inputs, and the Deutsch-Jozsa algorithm will still be able to tell you if it's constant or balanced in 1 step. Now, as I said before, this is kind of a toy problem. This problem was literally engineered to be as difficult, super difficult for a classical computer and super easy for a quantum computer. So this difference is very large, right? Exponential versus constant is almost the biggest difference you can come up with in a reasonable case. Even though the algorithm is not practically useful, this does give us an example of when quantum computers very clearly outperform classical computers. So just to kind of give you a chance to practice this particular statement or these particular facts, I have one last Zoom poll before we finish up for today. And that is asking you for 10 bits, let's take that as an example. For 10 bits, how many steps does the classical algorithm take? And how many steps will the Deutsch-Jozsa algorithm take? So go ahead, plug in your answer. And once everybody has voted, or once 50% of people have voted, sorry, then I will go ahead and say the solution. As I said, this is the last slide before I talk about key takeaways and summaries and that kind of stuff. So we are just about done here. I apologize for going slightly over time. Okay, so it looks like about 50% of people have answered. So I think just looking at the answers that have come in so far, people are in more agreement with the number of steps in the classical case. So in the classical case, I guess I should have said as well, these numbers are not exact, right? Just like in the search case, you could have different functions of f that are really fast to solve or really slow to solve. So all of this is talking about sort of the worst case, as we usually do in computer science. So in the classical case, we're looking at something that is big O 2 to the n. And so all we're going to do is take the number of bits, 10, and plug it into that formula. So 2 to the 10, if you work that out, is 1,024. So this should be the answer to the number of steps in the classical case. Okay, let's look then at the Deutsch-Jozsa case, right? Again, we're going to take our formula here. It's big O of 1. And then I plug in n, which doesn't appear anywhere. So we still just have 1. And it takes 1 step. That's it. So the answer here is that the Deutsch-Jozsa algorithm is only going to take 1 step. Again, this is a huge difference, right? And if you keep increasing the number of bits, this difference is only going to grow larger because the Deutsch-Jozsa algorithm is always just going to take 1 step. And that's why this is such a powerful demonstration of quantum advantage. Okay, let me just see. Yeah, so some people are confused about the exclamation here. That is not a factorial. That was just supposed to be an exclamation mark. So sorry about the confusion there. And somebody gave a slightly different bound for the classical algorithm instead of this order 2 to the n business. It turns out that 2 to the n in this case is it's equivalent to the bound that was given in the chat as well. I can talk more about why the bound given in the chat is sort of more precise, but the way that big O notation works is we usually just drop constant factors. I won't go into more detail on that, but we usually try and just sort of give the simplest possible expression, which in this case is 2 to the n. Cool. Okay, so that is the end of today. Let me go ahead and share the poll results as well. Some key takeaways before we shift over to optional content. Big O notation, we reviewed that. It's a way to characterize how many steps or comparisons or general computations an algorithm takes in the worst case, right? And so remember, we had that example of looking at worst, best, and average case. It's totally reasonable to do that. You can do that, and sometimes we do that. But big O notation is all about worst case. Linear search has a complexity of big O of n. The Deutsch-Jozsa algorithm solves a slightly different problem where the classical case has a complexity big O 2 to the n, whereas Deutsch-Jozsa, the quantum algorithm, has a complexity big O of 1. Just always takes 1 step, no matter what your value of n is. There's quite a few further readings this week, kind of because we stayed at a fairly high level when we talked about Deutsch-Jozsa. There's a lot more you can learn about how this algorithm works in detail. In that case, I would highly suggest this first resource here, the Qubit textbook, as I understand, has a really good description of how it works. And then there's a few other things here as well for you to peruse. Okay, let's pop up the post-lab Zoom feedback, and then I will take a break and shift over to optional content. So please let me know how you're feeling about these things. I guess just to reiterate as well, hopefully, this is one lab where I didn't try and explain everything in total detail, right? Obviously, we didn't draw the full circuit for Deutsch-Jozsa. We didn't walk through the math for it. That's okay, because we're not expecting you to know the full algorithm in great detail, right? What I talked about here is what we want you to understand. The most important points of Deutsch-Jozsa is just that it uses interference and superposition in order to achieve this quantum advantage. And hopefully that does make a bit more sense now. Okay, so I think I will pause here for just about 30 seconds. I'm going to go and grab myself some water. But when I come back, we will jump into some questions. As I said, there's no formal optional content, although I can think of at least 3 different things that would be fun to do in the optional content where we can dive into a bit more detail if you're interested. So when I come back, I will just start answering questions until the end of the lab. But if you do have to head off now, that's the end of the required content. So I will be back in about 30 seconds, and we'll get into student questions. Okay, so let's come back then for questions and optional content. Um, I am not going to attempt to go back through all of the questions in the chat. I think if you have a question, just feel free to copy paste it again in the chat box, and I will try and take a look. So one question I see just toward the bottom, does every gate, H gates or X gates, count as a step? Still unclear as to how complexity is measured in quantum. Yeah, that's a really good question. And I sort of skimmed over that a little bit on purpose because we didn't go into full detail on the algorithm. When you talk about complexity in computer science or in quantum computing, you usually do have to specify sort of what your unit of measure is, right? Like what computations are you actually counting? In this case, what we're counting is the number of function calls, okay? So in the classical algorithm, every time you feed in an input, that counts as a function call. In the quantum algorithm, every time you use that UF block, that oracle, that counts as a function call. So you're absolutely correct that if you did this for, let me just go back to the slide where I had the circuit diagram. If you did this for more bits, right, if you had like a 10-bit input, you would have more qubits at the beginning and you would have more H gates. That, that you could view that as counting as more steps, but usually the way that we look at quantum algorithms is just looking at the oracle, right? And so even if you had a 10-bit input, you would still only have one oracle, even though you would have more H gates. So hopefully that makes some sense. I guess in summary, when we talk about big O notation, we are talking about the number of function calls, which in the quantum world is the number of oracles we have to use. Okay, so somebody asks me in a direct message, would I be able to confirm the implementation of the balanced oracle in the notebook? Shouldn't there be 6 ways to implement f of x? Let me just see, check the notebook here. Okay, so in the balanced case, shouldn't there be 6 ways to implement it? I'm sure that there's different ways of implementing these oracles. I don't think that the text or that the notebook tried to enumerate all of them. Oh, I see. They're just following up. Just to clarify, I guess, these terms constant and balanced. Constant means that your function always outputs the same number, right? So if the outputs are always 0 or always 1, that's constant. Balanced is if they're 0, 1, or 1, 0. Okay, I'm not quite sure if I answered that question, but if not, feel free to post a follow-up. Okay, so somebody asks, the n over 2th element in a list will be at index n over 2 minus 1, right? Yes, possibly. So the reason I'm kind of being a little bit hesitant to answer this question fully is that, n over 2 could be a decimal number, right? And so to come up with a formal definition of exactly how many steps you would have in these list searching algorithms, you have to use the ceiling and floor functions, or you have to basically round n over 2, right, somehow. And without specifying exactly how we're doing that rounding, we can't really come up with an exact answer. So yeah, it could be n over 2 minus 1. It could be exactly n over 2. Not entirely clear given the specifications we have right now. Okay, so somebody asks, can you please explain how measuring x reveals whether f of x is constant or balanced? The qubits don't look entangled. So I guess the first thing I will say is that the qubits could be entangled, right? We're not telling you how this, or like you don't know necessarily how this oracle is implemented. For all you know, this oracle could be a Bell state preparation, right? It could entangle the x and y qubits before they get spit out on the other end. So this oracle could entangle things. It also might not entangle things. I think for this particular algorithm, though, you don't really want to think about entanglement. You more want to think about how superposition and interference create the answer. In order to see exactly how it works, we would have to walk through the math. I think the math of the Deutsch-Josza algorithm is kind of it doesn't really help with understanding that much, in my opinion. Maybe there's a good way to interpret it. But for me, when I learned it, and even now as I understand it, the math is there, it works, I guess, but it doesn't really give me any particular insight into why this algorithm works, besides the use of superposition and interference. I guess just to answer one other question, I guess this wasn't asked directly in the chat, but just to clarify the final step of this algorithm here, you measure the first qubit, right? So if you're doing this algorithm and you create this circuit on the IBM quantum experience for yourself, you will of course get 2 bits as an answer, right? So it might spit out and say, oh, your answer is 0, 1. For the Deutsch-Jozsa algorithm, we only care about the first one, right? And so that's why in step 6 here, it's saying only look at x. If x is 0, the oracle is constant. If x is 1, the oracle is balanced. Okay, this is another good question. How do we compose the algorithm if we don't know the function in the oracle? Yeah, so if you're going to go ahead and do this on the IBM quantum experience, you could just try each of the 4 possibilities, or you could pick one oracle to try and see if it works, right? So if you're creating this whole circuit by yourself, you do have to know what the oracle is to implement it, right? Again, this is kind of a toy problem, so I can't really come up with an example of how this might be useful in a real world scenario. It's sort of, yes, you have to create the circuit, but now you pretend that you don't know, if UF is constant or balanced. You can figure it out. But yeah, you have to come up with that. You have to pick which oracle you're going to use when you create the circuit. Okay, so somebody clarified their earlier question. They're asking about the total possibilities of f of x being balanced. Shouldn't it be 4? In other words, shouldn't it be 4 choose 2? So let's go back to the slide where we had all our possible oracles. And I guess they're asking, shouldn't there be more possibilities for oracles that are balanced? I don't think so, right? So as long as, well, I should clarify here. This is if your function only takes 1 bit as an input, right? So as long as we're looking at oracles that only take 1 bit inputs, these are the only 2 possible balanced oracles, just because these tables are so small, right? It only takes 1 bit input, it only has 1 bit output. There's only so many possibilities. So I think it should just be these 2. Okay. Yeah, so asking again about complexity, just to clarify, when we talk about the number of steps in a quantum algorithm, whenever we're talking about oracles and we talk about the number of steps, we're talking about the number of oracles you need in the overall solution. So in the Deutsch-Jozsa algorithm, you would need, order n, big O of n, H gates, for example. But no matter how big your input is, you're always just going to need 1 oracle. And so that's why we call it big O of 1. Okay, so somebody asks, where did I write this down? Here? Yes, okay. So somebody asks, what is the purpose of the H gate on the Y qubit after this is all done? I can think of, I'm actually not 100% sure off the top of my head. And I guess just to explain as well, I think the motivation for this question is that, well, if you don't care what the Y qubit ends up as, why do you have to do this gate, right? Couldn't you just not do anything on the Y gate and it wouldn't that make, or on the Y qubit, and wouldn't that make things simpler? I don't know for sure off the top of my head, but I believe it's the case that this would still work. Yes. The reason that we usually put this H gate in here is that when you go through the math, it's going to make things a little bit easier to see what's going on. But if you actually implemented it in a lab, I think you're right. You could just remove that and it wouldn't change the algorithm, but don't quote me. Okay, so another direct message here. Since quantum gates are reversible, it's impossible to make a quantum hash function. I guess. Yeah, so if the definition of a hash function that you're going for is a function that sort of takes many bits as an input and squishes it down to a smaller number of bits, yeah, you couldn't do that directly. I guess I should say that, yeah, maybe this is going into a bit too much detail, but we'll say it anyways. There is a way that you can do irreversible stuff in quantum. It's just, we're definitely not going to cover it because you usually only use this in, well, yeah, I don't know. I can't even think of an algorithm where you would use this. I remember we learned it at one point, but suppose you have some random unitary, right? So this is just going to be some big matrix. And let's say that it takes in 6 qubits, right? So 6 qubits as input. And suppose this is supposed to be some kind of hashing function, right? So maybe this is our U hash quantum hashing. We could keep the first qubits as some kind of hash, right? Some kind of hash state. Maybe that's how this works. The other 3 qubits, sometimes you'll see this drawn like this. And basically all this means is take those 3 qubits and throw them out, discard them. Let them dissipate as heat, let them, if they're photons, let them just fly off into the world. If they are electrons and an ion, let them just fall back to their natural state, whatever. It means basically just discard them, let them go back to the environment. And in this case, this is irreversible, right? Because once you lose these qubits to the environment, you might not be able to reverse engineer what the original inputs were. So I imagine if you were trying to do some kind of quantum hash function, you would do something like this, where you take some of your outputs and you just throw them away. But it's important to note that the quantum gate itself is still reversible, right? If you had not thrown away these outputs, then you would have been able to reverse engineer it. It's just because you chose to sort of discard some of the qubits you had that now it becomes impossible to reverse engineer. Okay, somebody asks, does the quantum state collapse when being inputted into the oracle? No, it does not. And that's important too. You need to have superpositions when you pass your qubits into the oracle. So if there was some kind of state collapse here, the Deutsch-Jozsa algorithm would no longer work because one of the fundamental things it relies on is, as we talked about, superposition. So you need superposition going into that oracle. The oracle itself, though, is just going to be some quantum circuit, right? So as some students were talking about in the chat, you can implement it with a C0 gate. You can implement some of the oracles just using an X gate. So at the end of the day, this is just a quantum circuit. And so there's no measurement or state collapse that happens inside of it. Yeah, so somebody asks, where can we use this in real life? Good question. I'm not aware of any examples. Again, the Deutsch-Jozsa algorithm is a toy problem, which just means that it was basically conceived, somebody thought of it as a way to show that quantum computers could do better than classical computers, which, as I remember another student said earlier in the chat, it's kind of like setting up a race where you are setting things up in every possible way to make sure that the quantum computer wins. And then we're all supposed to be super surprised and happy when the quantum computer wins. It's a little bit weird, but the Deutsch-Jozsa algorithm is pretty old as well. So this is one of the very first quantum algorithms that came out. And the reason it's important to learn about, and it's sort of an important part of quantum computing's history, is because it was the first thing to show, yes, here's a concrete example of an algorithm, or I should say, here's a concrete example of a problem that a quantum computer could solve way faster than a classical computer. And it's sort of the simplest example where you can see this happening. Okay, somebody asks, is it mandatory to apply X and H gates? I'm sure you could come up with variations on this algorithm that use slightly different combinations of gates. This is the most standard implementation. And with this implementation, for it to work as I've written, yes, you need to follow each of the steps. Okay, yeah, why don't I will verify this circuit that somebody is sending. I wonder if it'd be good. I can just open this up on my screen share, perhaps. I don't know. Yeah, sure, why not? Shouldn't take too long. Okay, so I'm going to go ahead and share my screen here. just in case anybody else doesn't have access to IBM Quantum Experience right now, this is what the student sent in the chat. This is the circuit. Okay, so this looks correct to me as far as the Deutsch-Jozsa algorithm goes. Just to, I guess, clarify, the way that I wrote it in the notes, I sort of had moved the H gate over here just to line it up with the second one. But the circuit composer is going to line it up like this. So we have our X gate followed by our two H gates. I'm going to throw in a barrier here just so we can, oops, I guess that's not a barrier. How do I do a barrier here? Oh, that is a barrier. Huh, okay. I'm not super familiar with how the composer works, but I guess just to mark it off, I'll do something like this. This thing in the middle here is the oracle, right? And so as I mentioned before, if you're actually going to do this as an example yourself, you need to come up with whatever oracle you're going to test, right? So in this case, the student has done a C0 oracle, which I believe, let me just think about that for a second. I think this is going to give us our third, oh no, okay, I don't know if I can do this in my head. It's going to give us one of the four oracles. Maybe they can tell me in the chat. Balanced, right? Is it going to give us the first or the second balanced one? Anyway, okay, doesn't really matter. But let's just say that we have picked oracle number 3. I don't know if that's actually what this does, but let's suppose oracle number 3 is the C0 gate. Again, we're sort of pretending that we don't know what this is. But for this one, we're going to test our third oracle. And then we have our two H gates at the end. And then we measure the X qubit, as we talked about. And if we scroll down here and look at what our answer is, you can see that the answer is 1, 1. Now, as I mentioned, we don't care about or actually, let me just remove this measurement to make sure this is working. Okay, yeah, we're good. Again, the reason I removed that is because when you're looking at the composer and you're looking at the state vector, usually you don't want a measurement in your circuit, right? The measurement is only important if you're going to run it on an actual quantum computer. So here our answer is 1, 1. Again, we don't care about what the second qubit is. We just look at the first qubit. And if you think back to the way that our algorithm works, it says that if this first qubit is 1, then our function is balanced. And so hopefully that's the correct answer for whatever oracle we're working with here. Yeah, so somebody's asking in the chat, the structure of the oracle can vary. Absolutely. In fact, one valid oracle is just nothing. So you can go ahead and try this yourself if you want. But we see here that this gives us 1, 0 as the answer. Wait, is that correct? Hold on. Let me just confirm here. So if you always spit out exactly, yeah, wait, this should give us, hold on. Now I'm confusing myself here. Okay, I feel like it's probably not wise for me to try and debug things live. When we run, we get 0, 1. Okay, 0, 1 is what I would expect, but why is the state vector showing me 1, 0? Oh, wait, is this right indexing? Oh my gosh. Yeah, okay. See, yeah, okay, I got confused by right indexing as well. Yeah, so remember that the way this is going to be listed out as an answer is qubit 1, then qubit 0, right? So 1, 0. So sorry, the qubit we care about is the second one as it's listed out here, just because of right indexing. So this is what I was expecting. It turns out it is a valid oracle to just do nothing. And in this case, you would get a constant function, which is an output of 0. Yeah, sorry, right, and as you could tell, even I get confused with these things, right and left indexing. Okay, so I think, yeah, hopefully this helps that student who came up with this circuit. Looks totally correct to me. Of course, you can change the oracle that you're doing in the middle to try out different oracles. So let me go back to questions. So I tried that circuit. Okay. So somebody asks, is the oracle more like a concept rather than a fixed algorithm or matrix? We use a certain version of the oracle for the kind of problem we want to solve. I would say the oracle is more like a concept. Yeah. So when you actually go and physically implement this thing, there is no, oracle gate that you can drag in the circuit composer, right? You're going to have to create the oracle out of actual quantum gates, which implies that you're going to have to come up with a particular oracle you want to test. The oracle is more a concept that we use in computer science to sort of simulate the idea that we don't know what's going on here, right? We know there's some kind of operation. We know it takes in qubits and it spits out qubits. And moreover, we know, if I switch back to my tablet for just a minute, moreover, we know that whatever this oracle is doing, it's going to do this operation, right? So it's always going to spit out x on the top. It's always going to spit out y XOR f of x on the bottom. We know that this is the case, but we don't know more than this, right? And so the oracle, I would say, yeah, maybe it's a good way to think of it as sort of like this abstract concept that simulates our lack of knowledge about what's really going on in there. If you want to do it on a real quantum computer, you have to, of course, tell it what exactly you want it to do. And then you have to pick a particular oracle. Okay, so somebody asks, if you do the Deutsch-Jozsa algorithm with 1 qubit, then a C0 will give balanced and no C0 will give constant. Yes, so those are 2 possible oracles. There are 2 other possible oracles as well, though, that involve X gates that will give you also constant or balanced as results. Oh, I see. Okay. So the person who was asking me questions earlier that I apparently didn't understand has clarified one more time. So they're asking how many ways, in how many ways can we make f of x balanced given that we have an n qubit input? Okay. So that we can do. Let's hop to the extra content. So again, just to set up the question here, this is just kind of a fun thought problem, I guess. If we have n qubit inputs, how many different ways can we make a balanced function? So just me thinking about this, I think the best way would be if we write out our bits. So we have x0, x1, ... and we have n bits of input, right? So we're going to start off with all zeros and a 1, and so on and so on. And eventually we'll get to 110, 111. Okay, so obviously not a complete truth table because I'm trying to remain generic here. Let's try and label some things though. So the first question I'll ask is how many rows are in this table? Right, if we want to record every possible arrangement of n qubits, how many rows, or sorry, n bits, how many rows are there going to be? Right? Yeah, okay, so somebody gives it in the chat here. It's 2 to the power of n. 2 to the n rows. Okay, now we're going to see, what our function is, right? So this is f of x1, x2, ... xn. So now our function f, we're pretending it's going to take n bits as inputs. Now, in the Deutsch-Jozsa algorithm, the function f always still spits out a 1-bit answer, right? So each answer here is going to be 0, 1, whatever, something. And these can be arranged in any order. And the question is, how many different ways can you construct an oracle that does a balanced output, right? So in order to do balanced, we basically have to pick 2 to the n over 2, so half of these rows that are going to be 0, and half of them that are going to be 1, right? But in terms of sort of how many different ways we can construct it, the only thing we have to worry about is how many different ways can we assign half of these rows to be 0, because then all the rest are going to be automatically 1, right? Okay, so once you know this, you're basically asking the question, how many ways can we select 2 to the n over 2, so half, which is just 2 to the n minus 1, how many different ways can we select that many elements from a list of 2 to the n? Okay, so at this point, you need to use combinatorics. So if you know what the binomial coefficient is, then you'll know what I'm about to do. If you don't, no worries. It's obviously not at all part of what we're talking about here. But there turns out to be a mathematical function for how you do this. And it is written as the following. You would do 2 to the n, choose 2 to the n minus 1. And it's just the binomial coefficient. So again, I think this is correct. I mean, I don't know exactly the answer, but I think this is about how you would do it. Okay, again, no worries if you don't know what this is. We haven't taught binomial coefficients. So, okay, so somebody direct messaged me a picture and they're asking me, is this doing the oracle? Let's see. Yes, that looks like a valid oracle to me. Yeah. So I guess just to explicitly do this, I do have some extra slides where we can talk about the various oracles. It just so happens. So, I mean, we've already seen a couple examples, right? The circuit I showed on the screen that the student sent is a C-naught gate to do the oracle. I also said that just doing nothing can be an oracle. So let's actually look at each of the 4 cases and see how you would implement them in quantum circuits. So first of all, case 1, this is a constant 0, right? Constant function always spits out 0. And we can go ahead and write down a truth table for ourselves, right? So I've just done x and y here, and then f of x, so always 0 for this particular version of f. And then we're going to look at our outputs. So the first output is always just a copy of x, right? So this looks the same as the first column, 0, 0, 1, 1. The last column here is the complicated one, this y xor f of x. And although it might not be immediately obvious, you could notice that this is the exact same as the y column, right? 0, 1, 0, 1. And so a valid way to implement this is to just take whatever your input is x and feed it out as your output. That makes sense. But your second output is actually just equal to y. And so this is the case I was talking about, where if you just do nothing, that is actually the first oracle. Let's look at case number 2, right? So I won't go into as much detail, but I've set up the same kind of truth table here. And now the question is, can you come up with some version of quantum gates that's going to produce this 1, 0, 1, 0? If you look at this table for long enough, you might realize that that is just the not gate applied to y, right? So 0 turns into 1, 1 turns into 0, 0 into 1, 1 into 0. And so here, we would again just do nothing to x. But for y, we would pass it through an x gate. So this is how you would do oracle number 2. Okay, let's look at oracle number 3. Exact same setup, and now the same challenge. How do you come up with some quantum gates that produces this last column here, 0, 1, 1, 0? So here it's a little bit less obvious, right? It's not really a direct function of y. It's not even really a direct function of x. Now we've already seen, I guess, hint, hint, we've already seen what this one is. This is the C-naught oracle. So if we sort of look at what C-naught of x and y is in each case, in the first case, we have, I guess in both of the first 2 cases, x is 0. And so we don't do anything to x or y, right? And so indeed, we don't do anything to y here. 0 goes to 0, 1 goes to 1. In the case when x is 1, we should be flipping y. So here 0 goes to 1 and 1 goes to 0, which is indeed what we're expecting. So the way to implement this oracle is to, again, do nothing to x. But now for y, we're going to do a C-naught. or I guess I should write this as y XOR f of x. Sorry, I think I wrote that incorrectly in the previous slides too. Yeah. Okay, now we just have one left. Case number 4. This is the most complicated one, but I think the thing that I would do here, look at the way this output list looks now. It's 1001. Does that look at all familiar or at all similar to this one, right? And hopefully you can see that it's the same, but we've just flipped all of the bits. So one way that you could implement this oracle is by doing the exact same thing we saw in the previous slide, a CNOT gate. But then we're also going to flip it. Just like that. So these are the 4 possible oracles for 1-bit functions. And as has been sort of discussed in the chat, if you go and implement this on the IBM Quantum Experience, for example, you need to pick which oracle you're going to implement, and then you just put in these gates, right? So you would, where this UF appears in the circuit diagram, you just sort of find this and replace it with whatever oracle you want to implement. Okay, so let's keep going through questions. Somebody asks a follow-up on my response about state collapse. So if there's no collapse in the circuit, maybe let me go back to the circuit diagram. Which one's here? Okay. So if there is no collapse, as I said, there's no measurement or collapse that happens before this oracle. Oh, I see. How can it be applied to a function which has bits corresponding to bits? Yeah, good question. So the way that I have defined this oracle is using, kind of pretending like we're using bits. Really what I should have done is always been using kets here. So all of these are just qubits. And I guess here we have one big ket, right? So all of these oracles, it takes qubits as inputs and it spits out qubits as outputs. Now, if you had a superposition, for example, coming in here, right, something like this, what you would do is split it up into 2 cases, right? If the input was a 0, my oracle would give this as the output. So in this case, for example, the output on the top here would be 1/√2 ket 0 plus ket 1. So it maintains the superposition. It doesn't collapse anything. It just, passes through the same value. Yes, so somebody says, so the structure of the oracle can vary, ? Yes, exactly. The structure of the oracle is these 4 possibilities, or I guess I should clarify, maybe there's different ways of implementing each of the 4 possibilities, but there are only 4 overall effects that you can do with this oracle. And you do need to pick one of them, and they are all different from each other. So somebody asks, does the oracle depend on f of x? Yes, exactly. So the oracle is always going to have this general structure that I've written on this slide, where the first input is just directly translated to the first output, and the second input is turned into this y XOR f of x thing. But of course, this last output here is going to be different based on what f of x is. And so, yes, this oracle does depend on f of x. Okay, so don't know why those aren't erasing, but okay. Anybody else have questions or things that they'd like me to go over? Okay, so somebody asks, is the oracle f of x? Not quite. So the oracle is the name we have for this whole block, right? So this big UF thing is the oracle. And so the oracle depends on f of x. It's not the same thing, though. So remember, the whole reason we introduced the idea of an oracle was to come up with a reversible version of f, right? So that is one thing I could say, is that the oracle in this case is a reversible version of f. but it's not exactly f itself. Actually, I missed one question above here. Somebody asks if case 3 of the oracle, so I'll just go back to that slide. If case 3 of the oracle could be implemented with a XOR, well, it is an XOR, right? All of these are XORs, but there's no XOR quantum gate. And so the question in these last 4 slides where I was talking about how to implement each of the cases for the oracle is asking, how do you do this with quantum gates, right? With your H gates and X gates and C naughts. And so here we use a C naught gate. Right? We don't technically use XOR. Can we have more than 1-bit function? Yes, yes. So this algorithm, I guess I've told you the 1-bit version, but if you go and read that Qiskit textbook page, it'll talk about how you can generalize this to an n-bit input, right? And so when I was sort of playing around with this question from the student here, how many possibilities are there for an n-bit input? This is what the problem looks like in general. Your f can take in an arbitrary number of bits, and it'll answer the same question though, right? It'll still answer if all of the outputs are 0 or 1, or if they're balanced. Half of them are 0, half of them are 1. Why is the big box called UF? U is just the letter we usually use for an arbitrary quantum gate because it's a unitary matrix. And then F is just to remind us that it depends on that function F. Could f of x be a machine learning algorithm like binary classification? Interesting. Yeah, I guess so. Just to clarify though, the requirement for f of x is that it must be constant or balanced, right? So this is a point that we didn't really have to talk about in the 1-bit case, but suppose we go up to the 2-bit case. So I have x1, x2, and then I have f of x1, x2. So let's look at this, right? Here is one valid f of x because it's constant, right? It always gives 0 as the answer. Another possible valid version of f of x would be something like this, 1, 0, 1, 1. If we had, 1, 0, 1, 0, because half the time it's 0, half the time it's 1. But f of x cannot be any random arbitrary function as soon as you go past 1 bit. So for example, an invalid f of x, an f of x where this does not work, something like this, right? This f does not work because it's not constant or balanced, right? It's obviously not constant because we have some inputs that give 0 and some inputs that give 1, but it's not balanced either because it's 3/4 of the time we get 1, 3/4 we get 0. Oh yeah, sorry, the last one here should be 1, 1. There we go. Yeah, so in order for it to be balanced, it has to be 50-50, exactly 50-50. So going back to your question about could this F be some kind of like machine learning binary classification algorithm? Absolutely, but you would need some kind of guarantee that it's either going to have the same answer for every single input, or it's going to give different answers on exactly half of the inputs. And I feel like that's a pretty tight constraint for a real world problem. Okay, so somebody asks, let me go back to my quantum circuit diagram up here. Somebody asks, so the second qubit, ket y, the second qubit is the ancillary qubit, and this is where f of x happens. What's the definition of an ancillary qubit in general? With n qubit Deutsch-Jozsa, you only have one ancillary. Exactly. Yeah, so if you were to expand this to a larger version of the circuit, it would look something like this. You'd have x0, x1, ... all the way up to xn. And then you would just have one y sitting here at the end. And then you would go and do an H gate on all of them. And then on y, you would do x followed by h. like this. And then you would have one big UF right here. Right? And then at the end, you would go ahead and apply all of your H gates again. Okay, and then the last part of the algorithm is still the same. You just measure the first one, and you get your answer for whether it's constant or balanced. So yeah, as you said, this ket y down here is what's known as an ancillary qubit, which basically means that, I guess, it's not, well, I'm not sure what the general definition of an ancillary qubit is. I guess, well, maybe the general definition, no. Yeah, I'm not sure. I'm not sure if there's a formal definition. I think the way that people usually use it, though, is if it's a qubit that's used in the computation, but ultimately you don't have to measure it. And so in this case, you would have a number of ancillary qubits. Okay. Actually, let me just double check one thing. I want to check that my circuit is correct here, because I have a bad feeling. I feel like I've done something wrong. Oh no, I guess this is correct. Okay. Yeah, okay. Cool. It's correct, thank you. Yeah, I don't know why. This looked weird for some reason, but I think we're good. Okay, so somebody asks, why can the oracle only be constant or balanced? The short answer is because that's the problem we set up, right? We engineered this problem in a particular way, like I said, to sort of show a quantum advantage. And it turns out that the algorithm we want here is one that differentiates between only constant and balanced functions. So somebody asks, at which step does x have the property to give the function as balanced or constant when measured? I see. So the only step at which it will have that property is after this final H gate. Right? So if you go and trace through this algorithm and see what's happening to these qubits all throughout, you will see that X is in a superposition once you come out of the oracle. And so you need to apply an H gate to put it back into the computational basis, and then you can measure it with certainty and get an answer. Okay, cool. So I think that's about the end of our questions for today. I guess if anybody else comes up with more questions as you look at this week's material or homework, feel free to post on Piazza. But thank you to those of you who stuck it out right till the end. Good luck on this week's homework, and we'll talk to you again next week. See ya.